Hi everyone, in this video we're going to be talking about graphing techniques, and this technique is called transformations. And so pretty much what we're going to be doing is we're going to be taking our library functions that we learned about last time. We learned quite a few graphs of these like library or parent functions, and we're going to be transforming their graphs. So just think about what that word means, transforming. So it starts with something that we have familiar, that's the library functions. And so then we take that graph and then we change it. We're going to transform it, transform the graph, and we form a new function from it. But it has the components of the original one. So what you'll see is it's going to be like shifting a lot of them. I'll mention it here. So we're going to be vertically and horizontally shifting. So it'll look like the same graph but just kind of moved up or down or left or right. Also, you can take the graphs and you can compress or stretch them, so it'll look like they got like smashed or stretched out. And then you can also just reflect, which is like flipping the graph. You can flip it over the X or Y axis. Okay, so let's jump right into this first example, and then we'll summarize the vertical shifts. So this first one's going to end up shifting up, and I'll show you how. So we have our original function. Notice this is our library function, square root of X. That's one of our library functions, and you always kind of want to just, in your mind, think about what that graph looks like before we do anything with it. That one I call the shooting star shape because it does something like this. So that's our graph of our square root function. We're going to use that original graph to get this new function, that graph, square root of X but plus 2, and then find the domain and range. And so pretty much the new function is just like the square root function, but what you're doing is you're taking all of the original values. Remember, f of x is y, so you're technically taking all these y values and you're adding 2 to them. And so what's going to end up happening is for every point on the original graph, it's going to move up 2 units in the y direction, and it's going to just look like a shift. So it looks like it shifts upward. And so the black one is the original one, and then every single point on the original graph for the new function, because it was square root x and then plus 2, it moves up 2 units. So if you can imagine, think of like just picking up this black graph here, the original one, and like moving it up 2 and then placing it back down to get this blue graph here. Now real quickly, before I get into the more examples of this, what I want to point out to you is when in doubt, you can always just plot points. So like, let's say you don't remember that this is that shooting star shape, and you don't recognize that this is going to shift up 2 units. And you don't have to recognize it yet because I'm barely teaching this to you right now, but eventually you'll recognize that this goes up 2 units. But let's say you don't recognize that. You can always just plug in points. So remember, when in doubt, you can always just choose numbers for x, plug them in, and you'll get out y numbers, and you can plot them. So for example, if you plug in 0, square root of 0 and then plus 2 is 2, and you would plot that point. And you can do that for all of these x values that you want. Plot the points, and you'll have enough points to be able to draw the graph. Okay, so pretty much for this one, like I was mentioning, all of your y values from the original library function are just shifted up by 2 units, or 2 gets added to them. And so it's identical except for it's just shifted vertically up by 2. And so the domain here is the same as the original function's domain. It's all positive numbers, including 0. And that's because originally, for square root of x, and for this new one that just has square root of x and then plus 2 on the outside over here, you can only plug in numbers 0 or more, because you can't take square root of negative numbers. It would be imaginary. So remember, just real quick off to the side, square root of a negative number, that's going to be imaginary, so we don't want anything negative. So 0 or more for the domain. And then the range, we can tell pretty quickly from the graph. Notice that because our whole graph shifted up 2 units, the lowest y value is 2, and then all the rest of the y values on the graph, it's going to keep going up eventually forever, and so it's going to go to infinity. So the range is 2 to infinity. And then one other quick reminder, remember you use brackets anytime you can equal those numbers. So when there's actually points there. So notice how we have a point right here at 2. That's why we have a bracket. We have 0 as the x value. We have a point at 0. So that's why we put a bracket there. Alright, so now, very similarly, but our new function is square root of x minus 2. So you can guess what's going to happen. It's pretty much the same shape, but it's going to go down 2 units. Every y value is going to just get 2 subtracted from it to form this new function. So the original y values, they're just going to get minus 2 applied to them, and then you'll see that the graph just looks like it got picked up and moved down 2 units. And so on this one, the domain didn't change again. It's still 0 to infinity from the original function f, but the range did change because notice now the lowest point on your blue graph is -2, and all of the rest of the points on your graph are going to go higher than that. They're going to go higher up to infinity. So -2 to infinity for the output or the range. So let's summarize that. This is the first of our transformations. So we're going to talk about quite a few transformations. That's what we're going over in this video. So how to transform a graph. And this is the first of our list. And it's vertical shifts. So if you take a number, a positive number, and you add it to your function, so you have your original f of x, and then you add a number to it, your graph is just going to shift up, vertically up, that same amount, whatever that number is. And then very similarly, but if you subtract the number from your function, then your graph is just going to shift down that same number of units. So this is our vertical shifts. So just before we move on to the next transformation, I'll just show you a quick example. So let's say I had f of x originally was, let's say, square root of x, and then our new one is g of x equals square root of x minus 1,000. It's the same shape, just shifted 1,000 units down. Okay, so now we're moving on to the next type of transformation, and it's horizontal shifting. And just like vertical, we could go 2 directions, up or down. And we're going to see that horizontal, we can go 2 directions, left and right. So we're going to use our parent function here, or library function. Remember, this is your absolute value function. So this one here is absolute value. Let me spell that right. Absolute value function. And remember the shape of that? It is the V-shaped graph. Okay? So we're going to use that graph. We're going to transform it and get this new graph where it's absolute value of x minus 2. So it's pretty much the same exact function. It's just going to be shifted, and then this time you'll see that it's going to shift to the right. And so let me just draw a line right down here. We have the original one. Remember, absolute value turns everything positive, and so we had our original one in black here, and then the new one, it gets shifted everything to the right 2 units. So when in doubt, you can just use this table over here. You can plug in numbers. You could say absolute value of 0 is 0 minus 2. That's -2. But then when you put the absolute value to it, you apply it, you get +2. And then you can do that for all your values, and you'll get this blue graph here. And so you actually move to the right 2 units. You pick up your graph, shift it over 2, put it back down. Or, I mean, since you can't literally do that, what you do is you just take every point on the original graph and you move each point one at a time over to the right 2 units. And you just do that for all of them, and you'll get your new graph. And so the x-coordinates on the graph in this example are just 2 units larger than the x-coordinates on the original function's graph for the same y values. Now the domain on this one, you can plug any numbers you want into absolute value, and then same thing, even though we subtract 2 in the new function, the domain is still all real numbers. And then the range, notice in both cases, but the one we're interested in is the blue one, our new graph, our lowest y value is 0, and then our graph goes up from there, so the range is 0 to infinity. So next example, we're going to shift this time, you'll see, to the left. So notice what's different this time. We have absolute value of x plus 2. And so it's pretty much the same shape as the original function, the v shape. And then you'll find out when we plot the points that it's going to look like it moved 2 to the left. And so when in doubt, you can always just plug in. If you're not sure what's going to happen, you can always just choose x values, plug them in, and you'll get the graph in blue. But if you know that this is going to end up shifting 2 to the left, and you're barely learning it now, so it's okay if you don't know it yet, but if you recognize that this is going to just shift 2 to the left, then you can pretty much just take your v from the regular one, the original, and just move it over 2 to the left. And so you technically do that for every point. So I know we're just doing it, we're looking at it here, but if you were to do this by hand, you would just take each point and you would just re-plot it 2 units to the left of what it used to be. And now the domain and the range, they actually didn't change. Even though we shifted left, it's still the same thing. We can plug in all real numbers, negative infinity to infinity. And then we didn't move up or down, so the range was still 0 to infinity. Okay, so here let's summarize this next transformation. So we talked about vertical transformations. Now we are talking about our horizontal transformations. And so to sum it up, if you have your original function and then you subtract a number from x. Okay, so notice it's inside with x. So f of, normally just x, it's f of x minus h. So if you subtract a number inside with x, your graph shifts horizontally to the right, that many units. If you add a number inside with x, then your graph shifts horizontally left that many units. So for example, if we had f of x equals absolute value of x was our original function, and our new one is g of x equals absolute value of x minus 7. Because we have x minus 7, it's this case here, this one's going to go 7 to the right, so 7 units right. I would have to put a 7 here to get back to just 0 in the center here, where x used to be. So the number for x has to get bigger, so that's why we end up going to the right with minus and to the left with a plus. Okay, so now let's combine the two things that we've been talking about. Let's graph this function, x minus 3 quantity squared plus 2, and then find the domain and range. So we're going to do it in parts. So notice the parent function or the library function, and this is what you actually want to do at the beginning of each of these transformation graphs. What is the parent function or library function? Okay, I like to call it parent in this situation because it's like, where did this one come from? So what is the parent function? And you have to sort of undo everything happening to it. So you're going to undo the minus 3, you're going to undo the plus 2, and then you'll recognize that the parent function is just x squared. Okay, so that's where we're beginning. This is the graph of x squared. This was one of our library functions. And if we just plot a few points, we know that 0 is squared gives you 0, 1 squared is 1, negative 1 squared is 1, and we have that standard parabola. And then we'll apply the two transformations to it, one at a time though. Okay, so if we just focus on what's happening inside with x, notice it's x minus a number. So just as a reminder from just a moment ago, x minus a number means that we're going to go to the right that amount. Okay, x minus a number goes to the right. Just so you have it here, x plus a number means that we actually go left that amount. Okay, so this is going to go 3 units to the right horizontally from our original function. So every point just moves over 3. So remember, it was 0, 0, and so we move that over to 3, 0. We had 1, 1, and so that moves over to 4, 1. And then negative 1, 1 moves over to 2, 1. And then we plot that parabola. Okay, and now let's apply the second transformation. So the plus 2 in the back, that looks like f of x plus a number, which goes up that amount. And then just a quick reminder, if it was f of x minus a number, that's when we would have shifted down that amount. Okay, so that one's going to go up from where we were just at 2 units. So we were down here at 0, 0 for this point that's called the vertex, this like center point. And we just take that point and we go up 2. And then we had a point over here, it was 4, 1. So we take that and move up 2. And then we did that for our other last point here. And then we complete the graph, and that's it for that transformation. And so the domain on this one didn't change at all the whole time from the original. Originally, you can plug in all real numbers, and you still can here even with this new version of the function. And then the range on this one, you can tell from the picture of our graph, but now that you kind of know, you can also tell back from the function itself. So notice the lowest y value is 2, so 2 to infinity, 2 to infinity for y. But you can now look back here and notice that it's your function, the plus this plus 2 part means that I'm going to start at 2 with my lowest part of my parabola and then move up from there. Next, we're going to be doing vertical stretching and compressing. So this is a new type of transformation, and we'll go through it. So our original function is again our square root one here. That's our parent function, and it's that shooting star shape. And we're going to graph a new one that's 4 times square root of x. And so notice what it's going to look like. And you can plot points always when in doubt, and it might help you especially on this one because you might not recognize what this transformation is going to do, but we'll sum it up here. Notice what you end up having. When you plug in 0 into the new function, it's still 0, so that point didn't change. But when you plug in 1, instead of having 1 as the output, you now have 4 as the output, because your y value, your output, got multiplied by 4. And then same thing happens over here when I plug in 4. Normally square root would just give me 2, but when I times that by the 4 on the outside of my function, I now have 8. And so what's happening here is your graph is actually stretching vertically. And it's still the same shape overall, but it's having this stretch applied to it in the vertical direction. And so all the y values are just 4 times as big as they were originally on the parent function. So all of your outputs, what it used to be, got multiplied by 4. So all of the outputs are now 4 times larger to form the graph of your new function, to plot those points. And so we call that vertically stretched by a factor of 4. Alright, so now let's do a vertical compression. So take a look at this one. Now notice your library function here. This is your square function. So just your standard parabola. So this is your square function, and the shape is our parabola. And so we're going to graph a transformed version of that by graphing 1/2 of x squared. And so all of your points on your original graph are actually getting multiplied by 1/2. So they're actually like getting cut in half. All your original y values are being cut in half or multiplied by 1/2. And so what ends up happening is that whole graph looks like it's going to be vertically compressed, or like kind of like smashed down, because all of your y values are now lower or shorter. And so this is the new one, the blue one. So you could take your original black graph here, and all of the y values get cut in half, and so it kind of looks like it's smashing down to get the blue graph. And so for example, originally if I plug in -2, I square it and I get out 4, but if I now I want to take that and times that by 1/2, and that's why now instead of a y value of 4, I'm down here at a y value of 2. And then this y value of 1, when I plug in -1, that's why I'm now at a y value of 1/2. And so all the points just kind of get cut in half, and so it kind of makes the graph look like it gets smashed or compressed. And so here is the summary of the next transformations. And so this is our vertical stretching and compressing. So vertical compression or stretch It's when your function is getting multiplied by a number. So it's going to look like this. And then depending on what the number is in the front, lets you know if it's a stretch or compression. So if that number is, think of this like a fraction, between 0 and 1. So like our example was 1/2. Then it's going to compress, like think of it as like smashing or cutting down your y values. If the number is bigger than 1, then it's going to look like it's stretching it. Everything's getting stretched out or larger. You're multiplying your y values to get them bigger. So for example, if you had y equals x squared, and then you have y equals 10x squared, then that graph's going to look like all of the y values got larger by a factor of 10 really quickly. So it's going to look like it's stretched vertically. Whereas if you had y equals 1/10 x squared, where all of your y values would look like they got cut into 1/10 of what they used to be. So it would look like they were smaller, or that your graph got compressed vertically. And so there's a similar transformation, and it's the horizontal version of what we were just talking about. So if we have a horizontal compression or stretch, it's similar in the nature of what it does, but I just want you to recognize that it's going to look a little different in your function. So it's when the number is multiplying the x this time. So just a quick reminder, on the vertical, it was when you had your number like kind of outside. So a times f of x, that was vertical. But this time, the a is actually in the inside with x, some numbers multiplying x and then getting plugged into the function. And so that's when it's a horizontal compression or stretch. And so two cases, just like with vertical, it's going to be a horizontal compression if a is bigger than 1, and you're going to be compressing by a factor of 1 over that number, so 1 over a. And then it's going to be a horizontal stretch if a is between 0 and 1, and it's going to be a stretch by a factor of whatever that number is, 1 over it, so 1 over a. So I'll show you an example on that one so you can kind of see it. So let's do this, and then I'll actually have us go over to a graphing tool to make it look a little bit more clear. So using our original function, which notice we don't actually know what it is, we're just kind of given the graph of it. And so f of x is the original, which is in blue here, and we're told to graph 3 times f of x and then f of 2 times x. So right away, this one, because it's a number outside multiplying f of x, this one's going to be a vertical something. So just by knowing it's a times f of x is vertical something, and then you look at the number. This one's a number bigger than 1, so this is going to be a vertical stretch. So just by looking at 3 times f of x, we can tell that that's going to happen. And then over here, notice the number's inside with x, so that's this case. So that lets me know right away that that's going to be a horizontal something. Horizontal, and this one's going to be compression. And that's because the number is bigger than 1, excuse me. And remember, this one is going to be by a factor of the reciprocal of that number. So horizontal compression by a factor of 1/2, which we talked about just on the previous slide, whereas this vertical stretch is going to be stretching by a factor of that number that we see right there, 3. Okay, so here's the original one, and you just kind of want to recognize the shape to be able to like transform the shape, and then some key points. So some of the key points that are labeled and some that aren't, like this one here, 0, 0, pi, comma 0, and then some of the ones that are labeled, and then that way you can stretch them and compress them as needed. Okay, so for the 3 times x, the 3 is outside, which we just recognized, so it is going to stretch our graph vertically. So like I said, I'm going to take you over to a graphing website to show you, but this is larger. It looks like it's larger in the y direction, so higher up going up and lower down going down, and it's stretching the graph by a factor of 3. So originally we had negative pi over 2 comma 2. This point used to be down here at 2, and then now it's all the way up here at 6. And then this one was just at -2, and now it's all the way down here at -6. So all the points got stretched vertically. And then for this one, we know that this is going to compress horizontally because the 2 is inside with the x. And so remember what we had? We had the point -pi/2, and so that point actually got, it's like, it looks like it went to the right. It didn't quite shift. It kind of got smashed toward the right, inward. And same thing over here. This point used to be over to the right more, and it got kind of smashed inward. And this point, remember, this was at pi/2, -2, and so it got compressed by a factor of 1/2. So think of it as like getting cut in half. What used to be at pi/2 is now pi/4. It's right here. So the compression, it's not quite a shift, because notice some points went left and some points went right. It's more of a like pushing inward from the left and the right, the compression. Okay, so here's our same original graph, and I wanted to plot all of the 3 graphs on the same coordinate axes so you can see the transformations a little bit better. So this is the original, and then if we times the whole function by 3, then we actually get this one here. So now let me zoom out a little bit so you can see that it looks like it's the same blue graph, but stretched way out vertically. So what was going up is going up way higher, and what was going down is going down way lower. So that's our vertical stretch by a factor of 3. And then the other one was compressing when we multiplied the inside of the function part by 2. So compressing by a factor of 1/2 horizontally. So that's this one. Notice it's the same blue graph, but just kind of smashed inward from the left and the right, if you can imagine that. It's getting compressed on both the left and the right horizontally. So I wanted to show you all 3 of these on the same coordinate axes, the XY plane, so that you can get a reference for how the original one got manipulated or transformed to form the 2 new ones. Okay, we are ready for our last type of transformations, and it's going to be called reflections. You can kind of think of this like flipping. So f of x equals negative square root x. All right, so the negative sign is going to do something interesting to our graph. And so this is pretty much the same square root function we've had a few times now, but it's going to be changed slightly, transformed, because of that minus sign. And so if you think about it, every original point is going to have an extra minus sign in the front now. It's getting applied, so like multiplying by -1. And so all of the original points, all the y values, all the outputs are now negative when they used to be positive. And so for us, it looks like the blue one here, it's just the black graph flipped over or reflected. If you can imagine like a mirror right here on the x-axis, then this would be where you are reflecting over, because all your y values that were positive are now negative because of this transformation. And this is just for this example that everything was all positive to begin with, and so it all became negative. But if you had a different example, just a side note here, if another graph had points that were both positive and negative, I'll just kind of draw this really quick. Let's say you had one that did something like this one here. Then all the points that were positive, let me just change colors on you really fast. All the points that were positive would come down here and be negative, but then all the points that were negative would actually flip and go up and become positive. So that's just to let you know, like that whatever was positive becomes negative, and whatever was negative becomes positive because of that extra minus sign right there that we're applying to the function. And so the domain of this one is going to be 0 or more, because it's our square root function, so that's the same as what we saw earlier, so 0 to infinity. And then the range on this one, notice now the graph technically goes down all the way forever to infinity, so the lowest y value is negative infinity, and then the highest y value the graph will ever reach is 0, so that's why it goes from negative infinity until 0 for the range or the y values. So then we have this transformation to add to our list, and it is a reflection across or about the x-axis. So pretty much if you see a minus sign in front of your function like this, you're multiplying by a -1, and so your graph is getting reflected, or you could say flipped, about the x-axis. Okay, so now there's another one. This one's going to reflect about the y-axis. So notice our function is -x and then quantity cubed. Okay, so to graph this one, the original function, the parent function, would be this one here. And we haven't seen this one yet today, but reminder that this is the cube function, and the shape of the cube function is like this river shape, if you remember that. So I like to call it a river shape. Okay, so every point on that original graph, notice what's changed. Your x is now negative, and that's getting cubed. So all of the x values, what was negative is positive, and then if they were negative to start with, then the negative that we're adding is going to make them positive. So pretty much they're all going to flip. Okay, so they're going to reflect about the y-axis. And so the new graph, -x cubed, is what's in blue. Okay, and so notice the mirror would be right here on the y-axis. Everything that used to be positive on the right has now moved to the left, and everything that was negative on the left has now moved to the right to become positive. So when in doubt, you can always just plug in numbers. You can always just choose x, plug it into your function, and see what you get out. So for example, if I plug in -1, I would get -1 gets plugged in right there for the x, just like this, but there was already a negative outside, and then that gets cubed, so that's 1 cubed, which is just 1. Okay, so when in doubt, you can always just plug numbers in. But if you remember that the original function was this river shape, and we had the point 1, 1, then you know that because this negative is getting applied to the x, then that's going to flip over the y-axis and become -1, 1. So the domain on the cube function and then this new one is all real numbers. You can plug anything in, there's no restrictions. And then the range, notice this graph goes all the way down to -infinity and all the way up to infinity. The range is also all real numbers. So this is another transformation. Okay, so this is actually our last transformation to add to our list. It's a reflection about the y-axis. So this time, if the x is getting negative, notice it's inside, the negative is inside with x, inside the f of x part, then we're going to reflect or flip over the y-axis. Okay, so now we're going to just do a few more examples because we've learned all of our transformations at this point and kind of just put them all together. And so for this one, we're going to start with the parent function of x squared, so our parabola, and we're going to apply these 3 transformations to find or create a new one. So we're going to shift 3 units right, we're going to reflect about the x-axis, and shift down 2 units. So our first transformation ends up making our function x squared look like x minus 3 squared, because remember, if we're going right, it's because it's x minus that number h, that's how many units we're moving to the right. So if we're moving h units right, so x minus h. Then we're reflecting about the x-axis, and so there's going to be a minus outside, out front of the whole function, so minus f of x to reflect or mirror about the x-axis. And then shifting down 2 units, notice that's just a -2 in the back because that would shift our graph down if it was x minus some number k, so we move that many units downward. And so this is a new function created from our original parent function of x squared with these 3 transformations applied to it. So same parabola originally, but we shifted 3 units right, flip it over, and then shift down 2 units. Alright, so now this next one, we're going to graph the function of x squared over 2 plus 1. So notice before we move forward, that the parent function or the original function is just the x squared. And so the x squared over 2 is more easily recognized as 1/2 times x squared. Okay, so that's getting multiplied by a 1/2, and then there's also that plus 1 in the back. And then step 1 is to graph our original function, so our parent function, our library function, which has just some key points on it: 0, 0, 2 squared is 4, and then -2 squared is 4. You can also plot 1, 1 and -1, 1 if you'd like, just to get those key points. And then we're gonna take all of those y values and cut them in half, or multiply them by 1/2. And so what was 2, 4 is now 2, 2. The y value got divided in half. What was 1, 1 is now 1, 1/2. That y value got cut in half right here. It's half as tall. This one's half as tall. And we do that for all the y values. And then from there, we're going to add 1. And so that one, again, is just this transformation of our function plus some number. So we're going to go up 1 unit, and so every point on the graph we just move it up 1. So the point that was at 0, 0 up here goes to 0, 1. This point right here, this is 1, 1/2, and so that point moves up to 1, 1.5 right here, and then 2, 2 moves up to 2, 3, and then we plot those. And you can actually just use symmetry to plot the other 2 points, just kind of match over on the left side. And so this is the new graph. And so because of the 1/2 getting multiplied, it is a vertical compression. So notice it does look a little more smashed down than the original parabola. And then the domain is all real numbers for any square function, x squared. And then the range on this one, we can tell from the graph. The lowest point right here is at 1, and then the graph just goes up from there. So that's why the range, or the outputs, is from 1 to infinity. Alright, for this last example, we're going to graph this function and find the domain and range. So notice what the parent or library function of this would be. It would just be the regular x square root x function. And then see the difference now from our original function and what we're given here. We have 3 transformations. So there's this 2 being added inside the radical with x, this plus 1 getting added in the back, and then this minus invisible 1 getting multiplied in the front. So we'll take each of those transformations one at a time. Let's start with the horizontal shift, and that's the inside part happening with x. And so that one, we can rewrite it. First, I would say that you could recognize maybe this as x plus 2. So from here, you could actually say that this is going to move left 2 units, or if you want to, you can just rewrite it one more time and recognize that this is x minus h. And so we're going to be going, so in this case, h is -2. So that's another way to recognize that we're going to go left 2 units. And then from there, we're going to start with the original square root parent function. So plot just a few points for your parent function, and these are some key points on that one: 0, 0, 1, 1, and 4, 2. And then we'll start applying the transformations. So remember what this one is. This minus in the front is going to reflect across the x-axis because it's negative times our function f of x. So all the points get reflected across the x-axis, or all the y values become negative. And so 0, 0 is still the same, but now this is 1, -1, and 4, -2. So that's one of our transformations. And then we had 2 more. So this one, we are going to shift 2 units to the left. So you can either recognize it from here as x minus h, h being -2, so 2 to the left, or you can recognize it from here as, if it looks like x plus 2, we're actually going left 2 units. And so all the points go left 2, so what was 0, 0 moves to -2, 0. What was 1, -1 moves to -1, 1, -1, -1, and also with our last point. Okay, and that is our second transformation. And then the third one is this plus 1 in the back, and so that is just going to be our function plus a number, so it's going to go up that amount, so up 1. And so all of our points, we had -2, 0, goes up 1, so -2, 1. And then -1, -1 goes up 1 point, and then same thing with our last point here. And then so this is our final graph. We transformed our original square root function, and by applying 3 transformations to it, we flipped it over the x-axis, we shifted it 2 units to the left, and then went up 1. And then the domain on this one, notice kind of what you could tell from the graph, or you can go back to the written function, that you can't plug in anything less than -2. From the graph you can tell that there's no graph to the left of -2, but from the function I don't want this to be negative, so it has to be x plus 2 or more, because I don't want to have an imaginary number. So either from the function itself or from the graph, I can tell that the domain should be -2 to infinity. And then the range, it's easiest to tell from the graph here that the highest y value on the whole graph is 1, and then the graph is going down forever, so it's from -infinity all the way up to 1 for the outputs or the range values. Okay, so we did it. We learned all of our transformations, and then we did a few examples with them. So just remember, based on what's given to you, we'll just kind of sum it up really quick. The way that the function looks, if it has a plus number outside the function like this, you're going up that amount. If it has a minus a number, you're going down. The whole graph shifts down that amount. Those are your vertical shifts. If there's something happening inside with the x, that one's going to be horizontal, and it's going to go left if it's a plus, and it's going to go right if it looks like a minus like that. Or you can factor out, like we did on this one, factor out a negative. So those were your shifts. And then you have your compressions and stretches. If you have the number being multiplied out front, that was a vertical compression or stretch. And if you had the number inside multiplying the x, that was horizontal compression or stretch. And then it was stretched or compressed depending on the number. Remember, if it was large, like bigger than 1, it was the stretch, and vice versa for the horizontal. And then the last ones were, if you had a negative, then it flipped or reflected your graph across the x or y axis. So this one would be all the y values get flipped, so that'd be across the x axis, and then this one, all the x values flip across the y axis. Okay, so those are your transformations of your graphs. So you want to know your parent or library functions, and then you can apply the transformations to get the new graphs. Thanks for watching.